Hey guys, it's Jerry Pinter. Welcome to Chapter 6, Part 2. In this video lecture, I'm going to talk about LRC passive filter design. And this is important for a couple of reasons. First of all, we're going to use a lot of the concepts that we've learned in the last few chapters and apply it to the design of a filter. And also, this is important information for your LRC filter project. Which is going to be to design, analyze, build, and test an LRC passive filter. So just a little review here. What is an LRC passive filter? Well, an LRC filter uses three components. L is for inductance, and this is a picture of a few different types of inductors. The one that you're going to use is actually not shown in this picture. R is for resistors, and C is for capacitors. And this is what's called a passive filter because there are no active electronic parts here. There are no transistors or integrated circuits or anything like this. Inductors, capacitors, and resistors are called passive circuit elements. So here's the contents of this lecture. I won't go ahead and read through these right now, but we're just going to go through these topics here in this video. So the first thing we're going to start with is the voltage divider rule. And again, this is something that I showed you guys earlier. I think it was in Chapter 3. But this is a really useful sort of a shortcut method to analyze what's called a voltage divider when you have two or more resistances that take a voltage like the input voltage here, and they basically split the voltage according to the values of R1 and R2, and this is the output voltage taken between those resistors. So this voltage here is basically divided, and this output voltage here, the ratio of the output voltage to the input voltage is given by R2 over R1 plus R2. So in other words, it's this resistance down here in this leg of the circuit divided by the total resistance when you add them together. And the key thing for us in this chapter is that this voltage divider works with impedances too. So suppose you have a circuit that looks like this, where you have some impedance here. This could be a capacitor or an inductor, and maybe you have a resistor in series with it. And then down here in this leg of the circuit, I'm showing two elements here, a resistance and another impedance. Again, this impedance, Z2, could also be an inductor or capacitor. And notice it's in parallel with R2. So the voltage divider rule says that we can immediately write the output voltage divided by the input voltage is given by this impedance here, which notice is R2 in parallel with Z2. And by the way, remember how to do impedances. Impedances or resistances, when they're in parallel, you take the reciprocal of the sum of the reciprocals. So this is just basic Ohm's law stuff from your physics or electronics class. And then on the bottom, we add up all the impedances. So we have Z1 and R1, which are in series, so we add them. And then we add that to this impedance, R2 and Z2, which again, of course, are in parallel. So this expression here gives us the output divided by the input voltage, and that, of course, is the frequency response. So this is the power of using this voltage divider circuit. So let's apply this to an LRC low-pass filter. Okay, so our example here, we've got this circuit right here. This is an example of an RLC low-pass filter. And by the way, for the filter project, if you're going to do a low-pass filter, you can't use this design right here. There's another architecture, though, that you can use. But this is the one that I'm going to work through in entirety, sort of as an example to show you guys how to do it. And you'll have to do it for a different circuit than this. Okay, so anyway, the trick is, we sort of did this back in Chapter 3, is we replace these circuit elements, the R, the L, and the C, we replace them with their impedances. So R, remember, it just becomes R. L becomes J omega L. And C here, the capacitor, becomes 1 over J omega C. So now we can write the frequency response H of J omega, which remembers is V out divided by V in. this is a voltage divider. So I'm going to use the voltage divider law. So I've got this down here, which is 1 over j omega c. Remember, that goes on top. And then on the bottom, we just have to add all of these. Notice they're all in series here. So I have R plus j omega L plus 1 over j omega c here. And the next step is just to kind of clean this up. Notice we've got fractions inside of fractions, so we can get rid of those by multiplying every term, top and bottom, by j omega c. So this on the top just becomes 1. This first term also becomes 1. And we have j omega c times r, which is j omega rc right here. And then this term here, j omega L, we have to multiply it by j omega c. So j times j, remember, is minus 1. So that we pick up the minus sign there. Then we have an omega squared, and we have LC. The last thing we can do here, which will just kind of make some of the analysis a little bit easier, is to remember that for any circuit with inductance and capacitance in it, the natural or resonant frequency of the circuit, omega naught, is defined as 1 over square root of LC. Okay, so again, this is just basic electronic theory. And so what we can do here is replace omega squared. We can replace that with 1 over LC. All right, and so when we do this, LC actually right here becomes 1 over omega naught squared. I should have said it that way. So if we square both sides here, you can see that LC is equal to 1 over omega naught squared. So what happens here is, here's the 1, which is out in front, and then this term here becomes omega squared divided by omega naught squared. So that's this term right here, omega over omega naught all squared, and then we have plus j omega rc. So this is the frequency response for this filter. And then, you know, to do our goal here next is going to be to construct a magnitude and phase plot. In particular, I'm going to show you the magnitude plot. So we're going to construct a Bode plot. And so to do that, remember, we need the magnitude of the frequency response. So notice, you know, in this expression here, this is the real part here, the 1 minus omega over omega naught squared. Those are all real numbers. And then this second part here, the omega rc, that's the imaginary part of this number in the denominator. So in order to find the magnitude of this function, we have to use the Pythagorean theorem. So we just take the real part squared, which is right here, plus the imaginary part squared. Okay, you know, you don't include the j, you just do the omega rc and you square it, and you take the square root of that whole thing. So that's why there's the power of 1/2 here. So this is the magnitude of the frequency response, which is what we're going to use next. So our next step is to find the 3 Bode plot asymptotes. So remember from part 1 of this video, we showed for a much simpler filter, the RC filter, how to find the low frequency and high frequency asymptotes. So we're basically going to do the same thing here. So, you know, if make sure you remember how to do that in part 1 of this lecture before we try something a little more difficult. So here's what we do. Remember, to find the Bode plot asymptotes, we have to find, convert them into decibels. So we have to take 20 times the log of the magnitude of h. So I have 20 times the log of the result from the last page. And the result from the last page is shown right here. Notice the power here is -1/2. That means we have a square root that's down in the denominator. Okay, so I'm just doing some algebra here to write this in a simpler form. And now I'm going to use my rules of logarithms. I'm going to take this -1/2 and bring it out in front and multiply it by the 20 to get -10 times the log of all this stuff in the parentheses here. Okay, so this is the full, we haven't done any approximating yet. This is the full expression for the decibels of the magnitude of the frequency response. So now let's do some approximations here. Let's first find the low frequency asymptote. So this is found easily by just letting omega go to 0 for low frequencies. So if we look up here in this expression, what do we have? Well, the second term has an omega in it, so obviously this term is just going to go to 0. Inside the square brackets here, I have 1 minus, and there's my omega, and remember that's going to go to 0. So this is 1 minus 0, which is just 1. And then we have 1, notice it's squared, but 1 squared, of course, is still 1. So what I have here is negative 10 times the log of 1, and that, of course, is 0. So this tells us that our slope, first of all, it's 0 decibels at low frequencies, and also it's constant. There's no slope. This is just a horizontal line at 0 decibels. Now let's go to the high frequency asymptote. So to do this, I set omega, I let it be very large. All right, now what we have to do here is, notice, let's do this part first. Inside these square brackets here, I have omega squared and then a 1 here. Well, obviously, omega squared, when omega goes to infinity, is much, much larger than 1. So we can ignore the 1. So this term here becomes negative omega squared squared, which is omega to the 4th. Okay, so we'll keep that in the back of our mind. Over here, I've got an omega that is squared, okay? But think about this. I've got omega to the 4th power, and I'm adding to that omega squared. Well, omega to the 4th is much, much larger, especially since, remember, omega is very large now. So what we can do is just ignore this last term here because it's going to be small compared to this omega to the 4th power here. So my result then for high frequencies is, in decibels, 20 log of h is equal to negative 10 times log of omega to the 4th omega divided by omega naught to the 4th power. So let's take that 4, bring it out in front. So I have negative 40 times log of omega over omega naught, and then I'm going to use another log property here. This is division of two numbers inside a log, so that becomes a subtraction. All right, so this first term here is negative 40 log omega, but then we have minus a negative 40, so that becomes plus 40 log of omega naught. And remember from what we showed in part 1, the way to find the slope here is whatever number is in front of log omega, that is the slope of the graph. So our slope here is negative 40 decibels per decade. All right, so it's a line that's going to go down at a very fast slope of 40 decibels per decade. Now, for second order filters like this, there's actually a third asymptote, because notice what happens here near the natural frequency omega naught. We get a different asymptote here. So if we get, again, if we go up here and look at this, when omega is close to omega naught, this first term falls out because we have 1 minus 1, which is 0. So all that's left then is omega RC all squared. So this is the third asymptote, and we can call this this is low frequency, this is high frequency, this is the mid frequency asymptote, which occurs when omega is near the natural frequency. So what we have then is 20 log h is equal to negative 10 log omega RC all squared. Take this 2, bring it out in front, and we have negative 20 times log of omega RC. And now let's split this up using, again, just basic log properties here. So we get negative 20 log omega minus 20 log of RC. And again, we can find the slope immediately by looking at what is in front of the log omega. And so this minus 20 here tells us that the slope is negative 20 decibels per decade. So again, if any of this, if you're wondering, like, what the heck am I doing here, please look back on part 1 of this chapter 6 video, because we went through examples of how to do these types of approximations and also how to find the slope on the Bode plot, which is a log-log plot. So we've got our 3 asymptotes here. Now the other thing that's different here is there are actually 3 corner frequencies where each of the 3 asymptotes intersects the others. And these corners are found by equating the asymptotes and solving for the frequency. All right, now the one exception here is that the notch filter actually has 4 asymptotes and 3 corner frequencies. All right, so let's look at a summary of what I just did. We have found 3 asymptotes, low frequency, mid frequency, and high frequency, and they are all listed here. This is just the results from the previous slide, and also I put the slopes here. And we can find the 3 corner frequencies, which are the intersections of these asymptotes. So in other words, to find the low mid corner frequency, we take this expression right here, 0, and set it equal to this expression, the mid frequency, and we solve for omega. And that corner, it turns out, for this filter is 1 over RC. Next, we can find the low-high corner. How do we do that? Well, we take the low-frequency asymptote, 0, and set it equal to the high-frequency asymptote, which is this expression right here. And again, we solve for omega. And after you do this, you'll find that the low-high asymptote is equal to the natural frequency of the filter, which is 1 over the square root of LC. Finally, there's one more corner. That's the mid-high corner. So this time we take this expression here and we set it equal to this expression down here. So basically we're just finding the intersection of these 2 lines. And this corner for this filter turns out to be R over L. So it turns out that these 3 corners will appear in any LRC filter. However, the filter that you choose may not have them in this order. In other words, this one up here might be R over L, and this one down here might be 1 over RC. So you'll just have to find those by actually doing the math and just setting these equal to each other. Again, just like we did back in part 1. So please refer to that if you need a little review on how to find these corners. So now that we've got the 3 asymptotes and we've got the 3 corner frequencies, it turns out that 4 different cases arise depending on the locations of the corners. So let's start with this first case, is when we have a large value of R, then 1 over RC will be a small number, and R over L will be a large number, right, if R is really big. And the natural frequency, 1 over LC, will fall in between them. So what happens then is we end up with a Bode plot that looks like this. The first corner, 1 over RC, will be way over here, and this will be the natural frequency right here, and we have R over L here. But what happens is if we look at this plot here, we want this corner to fall off quickly, but it falls off real slowly at -20 decibels per decade until we get here to the second corner, and then it finally starts dropping at -40. The reason for this, in part, is because when R is too large, the filter is basically overdamped. And you can see what happens here in the linear plot. This is not a Bode plot. This is just a plot of h of j omega magnitude versus frequency. Actually, I plotted it in hertz here. And you can see, this is the pass band up here at 1, but it's very narrow. We want this pass band to extend farther out to the right, especially for this application for your project. You're going to build an audio filter for audio frequencies, and so you're going to want the corner to be something that we can hear with our ears, and this is just way too low. So in summary, this result here, it has too soft or slow of a frequency response. This is not much better than a first order filter, because remember, a first order filter falls off at 20 decibels per decade. So let's go on to the next case. So in this case, let's suppose that we lower R, the value of resistance, but we actually go too far and we make R too small. So now what happens is R over L is very small, right? Because R is small compared to L. And 1 over RC is going to be large because R, which is small, is down here in the denominator. So these 2 corners have flip-flopped. They've changed positions. And this is the natural frequency corner right in the center. So what happens now is you get sort of a weird positioning of the 3 asymptotes. And at the resonant frequency here, the natural frequency, remember the filter has to go up to the natural, the mid-frequency asymptote. So there's this weird artifact here. The filter has a hump right at the corner. All right, and look at how pronounced this is over here in the linear plot. Remember, this is the log plot, so the hump gets sort of suppressed by the log scale. But the linear plot, remember the low-pass filter is supposed to have a pass band at 1, but this thing jumps up to 7. All right, so what's actually happening here is we have too small of a resistance, so we have underdamping going on here. The filter is underdamped, and we have resonance happening at the natural frequency where the filter actually boosts the input signal because of this resonance. So, you know, the good news for this filter is it does have a nice sharp fall off at negative 40. But the bad news is this hump here is probably not desirable because it's going to actually amplify the signal at the frequencies near the corner. So what's the best case then? Well, I'm going to show you two good solutions to these problems. The first one, if we set all 3 corners actually equal to each other. So in other words, R over L is equal to 1 over square root of LC, which is also equal to 1 over RC. Now, how do we get that? Well, all you have to do is choose a value of R that's equal to the square root of L over C, and this will happen. So look at all these asymptotes. Those are the blue lines. They all crisscross right here at the natural frequency, and that is also the corner of our filter. So this is a good filter now. Notice, you know, it has a slight hump here, but not that bad. It goes up to about 1.1, so it has, you know, it's only amplifying by about, you know, 10% there, or, you know, however you want to say that. So there's just a slight amplification, and the good news is this thing falls off nice and steep after the corner, and it's dropping here at negative 40 decibels per decade. And so this is an example of a good design for an LRC low-pass filter. And by the way, this design here is called a Chebyshev Type 1 filter. And you know, there's always trade-offs in filter design. So this one has a really nice sharp slope right here after the corner, and the only, you know, downside is there's just this slight little hump here at the corner, but for an audio filter that is usually not even detectable, something this small. So this would be a good design to use. There's one other case where you have the 3 corners obeying this relationship here, and this is found by setting R equal to square root of 2L over C. The one on the previous slide was just L over C. And so what this does is it does separate the corners a little bit, but as you can see here in the resulting plot here on the linear scale, this is what they call maximally flat. This filter is perfectly flat on top, and then it starts to roll off. And so there's no hump here. And so this is called a Butterworth filter, and this is also an excellent filter design, just like the one on the last slide. The trade-off here is, you know, there's a little bit of a softening here on the corner because it doesn't just start to drop at 40 decibels per decade until you get basically to this second corner, but these 3 corners are pretty close to each other on an actual filter. You know, I just sort of separated them here just to show this. And, you know, the advantage of this, of course, again, is that there's no hump at all. So this is the perfectly flat filter on top. So either one of these, you know, case 3, the Chebyshev filter, or this case 4, the Butterworth filter, would be good designs for your filter project. So here I'm going to show you a really useful tool to use for the design and analysis of your filter, and that is an Excel spreadsheet model that models the filter. And so you're going to have access to this, and you can modify it for your own filter. So this model, by the way, is on Cougar Courses in the filter project folder, and you can download a copy of it, and then you can modify it for your own filter. And what you do is, on this spreadsheet, all you have to do on these first 3 cells right here is enter the value of L, R, and C for your filter. So, you know, before you actually build your filter, you can try different component values here and make sure your filter is going to work as planned before you actually build the thing. And the other thing you'll have to do here, of course, is you're going to have to enter the formula for the magnitude of h of j omega, because that's different for each design of filter, depending whether you do low pass, high pass, band pass, or notch. And also, each of those filters, there are two different architectures. There's a parallel and a series architecture. So there are a total of 8 different filter schematics, basically, for an LRC filter, and they each have a different formula for the frequency response, like I just showed a couple slides ago. So what you do, if you're familiar with Excel, you go in here, this is the column for the magnitude of the frequency response, and you click on that cell right here, and you will modify this formula. This is the Excel formula for this particular filter that I'm analyzing, but the one that you're going to build is going to be different. You're going to have to enter different columns here. So I'm assuming that you know how to enter formulas into Excel. If you don't, you can look that up. It's not that difficult. These like E2 and G2, those are just the variables. Those are the cell names. So E2 is column E, row 2, so that represents omega. G2 is over here, that's omega naught. And what else we got there? There's E2 again, and then we have B2 and C2. Well, B2 is R, C2 is C. So all of these terms here come from the formula that you're going to derive when you use the voltage divider rule to find your frequency response. So the nice thing about this is all you have to do is just type the value of L or R, and it will automatically plot the Bode plot. And you don't have to copy it all the way down. You can just type it in the top cell, and it will automatically fill in. So it goes really quick to look at different values and how it affects. So what this model does is it plots, this is the Bode magnitude plot. You can see this is our low pass filter. It looks like I set the values for a Butterworth filter. Notice it's perfectly flat up here. There's no hump. And this is the linear plot over here. This is a Bode plot here. This is a linear plot here. So this is real handy, and you can also use this to produce and generate plots for your report that you're going to submit for your filter. Let's see, anything else? I guess that's the main thing for here. Oh, the other thing is there's a formula here for the phase of h of j omega, which we haven't talked about much, but this Excel model will also plot a phase plot for your filter. And it also shows a couple other things, such as the 2 corners, R over L and 1 over RC. It just calculates those depending on the values that you put in here for L, R, and C. It also calculates, obviously, the Bode plot. It's calculating, it's automatically figuring out how many decibels and plotting it accordingly. Okay, just real quick, I want to show you something else. Part of the filter project, you're going to determine the impulse response for your filter. So in order to find your filter's impulse response, I'm not going to go through this in great detail right now, but I'll just show you a quick outline of how to do it. So you start with your filter frequency response, like I had, from a few slides ago. And then basically what you're going to do is factor the denominator. Okay, so you're going to write this as 2 factors here, and these roots, P1 and P2, are given by the quadratic formula. So this is no different than how you would factor a quadratic here. And after you do that, you're going to break this thing apart using partial fractions into 2 terms. Okay, I call them A and B. Figure out what those expansion coefficients are, and then once you've got that expression for h of j omega, by inspection you can write the impulse response h of t. Remember, that's just the inverse Fourier transform, and you can do that using this transform pair here, like we did many times in previous chapters. And so when you're all done, it might be a bit messy at first, but it'll eventually boil down. And you can use Euler's formula, and you should be able to turn some of those complex exponentials into just sines or cosines. So for this particular filter, the impulse response, it has some term out in front, and then it has a decaying exponential term. So it's e to the minus t times some r over 2l, and that produces this decaying envelope right here. And then this part of the impulse response, the sine of omega t, of course, that is the oscillating part. So that's the red part that oscillates up and down, and the oscillations are damped, notice here, and so over time they diminish. So this is what would happen if you put an impulse into your filter, like a voltage spike. Your filter would actually sort of ring like this, but it would ring down and eventually come to zero because it's a stable filter. I want to real quickly show you probably the easiest way to find the differential equation for your filter. There are different ways to do this. You can certainly use things like Ohm's law and Kirchhoff's voltage law and so forth. We did something like this, I guess it would have been back in chapter 2, I believe, where we found the differential equation for a circuit like this, and I showed you several different methods on how to do that. So if you're welcome to use that in your project, but there's a much more simple and elegant way to do it using frequency response methods. So what you do is start with a frequency response for your filter, and we just showed how to do this a few slides ago using the voltage divider rule. So this was the result that we got, and what I'm going to do here is rewrite this. So I'm going to get rid of the fractions here. I'm going to get rid of that omega naught squared underneath there. The way I can do that is just multiply every term top and bottom by omega naught squared. So I get this, omega naught squared over omega naught squared plus j omega squared plus j omega naught squared RC. Now this term here, I did a little trick here. You have a minus omega squared. What I did was I turned that into plus j omega squared. It's the same thing, right? Because j squared is -1. So why did I do that? Well, I did this because we're going to use, we're going to go by inspection and turn this into a differential equation. So you'll see that in a second. The last thing I'm going to do here is this last term is kind of messy here. Remember that omega naught squared is equal to 1 over LC. So this becomes RC divided by LC, which is just R over L. So this is the final form that I'm going to use here. So now we can find the differential equation by inspection of h of j omega. So this is something that, again, we did this back in chapter 4 when we learned about Fourier transforms and frequency response. So what you can do here is remember the top of the frequency response tells you what's on the right side of the differential equation. In other words, the x terms. So there's no, all that's up here is just a number. It's omega naught squared. So this just becomes omega naught squared times x. On the bottom, the omega naught squared becomes omega naught squared y, right? Because this determines all the y terms. A j omega squared, remember that means there's a second derivative, so that we have a d squared y over dt squared, second derivative of y. And then here we have r over L times j omega, and remember j omega gives us a first derivative, dy dt. So finally, I can say that, remember for this filter, y is the output, that's v naught, or v out, I should say, all right? And then x, the term over here, well, that's the input of a system. So that's our vi. So I'm going to rename y to v out and x to v in, and I'm just going to put these terms in a little different order here. So I have second derivative of v out plus r over L times the first derivative of v out plus omega naught squared times v out is equal to omega naught squared times v in. This is the differential equation for this low-pass filter. I want to share with you a few practical aspects of filter design, in particular for this LRC filter that you're going to be building and designing. So the basic strategy to design the filter is to select the center frequency. And the center frequency, if you look back on those Bode plots that I just showed you, the center frequency and basically the corner frequency of the filter is going to be the natural frequency, which is, this is in radian. Remember, this is radians per second, is 1 over root of 1 over LC. And in hertz, of course, you have to take this and divide it by 2 pi. So you want to pick a center frequency that is in the audible frequency range. I would recommend something around 500 to maybe 1,000 hertz, something like that, is a good frequency to use for your corner frequency. And then you can choose R to specify the outside corner frequencies. Again, this will depend whether you're going to use that Chebyshev design or the Butterworth design that we talked about earlier. And then use the Excel model. And plug in. You'll have to do some work first to figure out your frequency response. But enter that into the Excel model, and then use that model to help you design and make sure your filter is working as needed before you actually try to build it. I won't go through details here because I'm assuming that you already have the skill set to find the magnitude and phase of the frequency response on an oscilloscope. But basically what you're doing, remember, the frequency response is the output voltage divided by the input voltage. So for magnitude, you're going to be looking at the amplitude of, let's say this is the input, this brown curve here is the input signal that you're putting into your filter from a signal generator, all right? And you're going to do this in your project. So on channel A, you would measure the input voltage going into your filter. And then channel B, on the oscilloscope, you're going to measure the output voltage. That's here, V out. That's in green. So your frequency response magnitude is just the ratio of the output voltage, in other words, the height of this peak right here, that's A out, divided by the height of this peak here, which is A in. And that tells you what your magnitude is for this particular frequency. And for phase, you can measure the shift here in time between these two plots and divide that by the period and multiply by 2 pi, and that will give you the phase in radians. So this is, these are just some basic things that you need to do in order to measure and construct the data from your filter and compare it to the theoretical curves. One other thing is to beware parasitic inductor resistance. So an inductor is a coil of long, thin wire, but they can have a considerable amount of parasitic series resistance. So, we think of an inductor, an ideal inductor, as having no resistance at all. But an inductor actually has a series resistance added to it because of all that wire that's coiled up inside the inductor. So, there's a couple tricks here. One is to make sure the resistor in your circuit is a lot larger than this parasitic resistance. And what you're going to use is the inductors in your kit are going to have relatively low in resistance, parasitic resistance. They'll have somewhere between 5 and 10 ohms, which is pretty decent, and that won't affect your filter's performance that much. Recommended components, I'll talk about this with you guys more later in the course when we start talking about the kits that you're going to be using. But for what I used, and I'm going to show you some results coming up, I used a couple of these 10 millihenry inductors, and you'll have some of these in your kit. I connected them in parallel to give, when inductors are in parallel, it's like a resistor. You end up with 5 millihenries. And each of these had about 10 ohms of the ones that I measured. So in parallel, the resistance would only be 5 ohms. So that's pretty low. So that's almost, that's pretty close to an ideal inductor. And then for capacitor, I'm using a 10 microfarad capacitor. So you'll certainly have one of those in your kit. And you can use other capacitors in parallel with it to change the capacitance if you want to. But in other words, a 10 microfarad capacitor and a 5 millihenry inductor, by putting two of these in parallel, will get you a natural frequency of around 700 hertz, which is perfect. That's right kind of in the audible level where you want to have it. And then, for resistance, you're going to that will depend on the design of your filter and so forth, but for most of the applications, you'll probably be using a fairly low resistance. I think I used 22 ohms or something like that for the ones that I'm going to show you next. Here's another practical aspect. beware amplifier clipping when you do your sound demonstration. So the idea here is that the signal generator output that you feed into your filter, it needs to be small enough so that the amplifier signal doesn't get clipped. So what I mean by this is if you put this signal right here into your amplifier, well, that's a perfect sine wave, all right? But your amplifier is going to amplify this by many, many times. And so what happens here is this amplified sine wave actually gets clipped off because the voltage of the battery in the amplifier just isn't large enough to show the whole thing. So, and here's a plot here. This is showing the input of the amplifier in yellow, which is a perfect sine wave. But look at the output of the amplifier. It's not a sine wave at all. It's a square wave. And a square wave has lots of harmonic distortion. And so it'll sound, you can kind of tell it has sort of a tinny sound due to all that harmonic distortion. So the solution to prevent this clipping here in your audio demonstration, because you want to show that the volume of your filter changes with frequency. And if your amplifier is clipped across all the frequencies, you won't hear any difference in volume, because you want to actually make sure these peaks here of the output are within the range of the amplifier's battery. So the trick is to use very low amplitude on the signal generator. So this is going to come from your kit, basically the signal generator that you use. I'll talk about that later with you guys as well. But you'll want to set it to a real low voltage. You don't want to be putting 5 volts into your filter. 1/10 of a volt or even less is probably best here. Another thing is beware loading effects. You can't connect like an 8 ohm speaker directly to your filter, because that 8 ohms is now going to appear in the circuit of your filter, and it's going to vastly change the performance of your filter. So what you're going to do here is basically you're going to use an amplifier, and I'll talk about that next. So you're going to use one of these amplifiers. It'll be something like this to connect it to the output of your filter. So here's kind of your setup. You have a signal generator, and this can be a standalone signal generator, or it can be one that's built into the PC in your analog discovery kit, for example. That signal generator puts a frequency signal into your LCR filter, and then the output of your filter connects onto one of these audio amplifiers. And the idea here is these amplifiers have a very high input resistance or impedance. It's usually much larger than 10,000 ohms. And so this will not load down your filter at all. All right, not much current goes into this amplifier. So that's really the only way to properly test this audio filter. I'm going to skip over this slide because this shouldn't be an issue if you use the analog discovery kit. However, if you're using a standalone signal generator, they typically have a 50 ohm built-in source resistance. So if you connect this up to your filter, then what happens is this 50 ohms becomes part of your filter. And that's not good, because that's going to change the characteristics of your filter. So one way to get around this is to try to make this signal generator look more like an ideal signal generator, which has no resistance at all, just like a perfect battery. So the way to do this, if you're using a standalone signal generator, is just to put a 1 ohm resistor across the output terminals. And this will create a voltage divider, which will give you a low voltage, which is good, so you don't clip your signal. And it produces basically a 1 ohm source resistance here. So your filter, basically all it sees then is more like a perfect voltage source. Now, if you're using the analog discovery kits, it turns out that they have a very low source resistance here. So you don't really have to worry about this trick. You can just connect it directly to your filter. Here are some suggestions for the audio demo. I'll let you guys look over this on your own when it comes time to test the filter, but basically there are some neat tricks to show how your filter works by sweeping the frequency to listen to the volume change as the frequency changes, and also put a little bypass switch or just a little wire where you can turn the filter on and off, back and forth very quickly to listen to the difference in volume for when your filter is connected and when it's bypassed. Okay, the last thing I'll do here, and again, I'll go through these real quick here. I want to show you some of the results that I got from building the LRC filter that we just described, and I went through and I actually built them all, and they all turned out very well. So what I'm doing in these slides, I'm going to show you the Excel model, in other words, the theoretical output of the filter versus my data that I actually collected with an oscilloscope. And I looked at all 4 types of filter: low pass, high pass, band pass, and notch. And I used both parallel and series architecture. So I built all 8 filters that you could possibly build for this project. I built them all, and they all work great. Let's see, what else should I mention here? So I was using 22 ohms for R. I used 5 millihenries for L and 10 microfarads. I say approximately. I actually measured those values on a meter, and they're a little bit different, but close to that. And my natural frequency is around 800 hertz. So here are the low-pass filters. So this is what I call a series architecture here, and this one is a parallel architecture. Now, you can't use this one here because this is the one I just analyzed in this lecture. But if you want to do a low-pass filter, you can build this one here. And notice in this graph here, so these aren't Bode plots, these are just linear plots of frequency response magnitude versus frequency in hertz. And the blue solid line is the Excel model. So that's the theoretical output of this filter. And the red dots are my actual data that I collected from the curve tracer. So you can see there's excellent fit between the data and the theoretical model for both designs here. Here are the high-pass filters that I built. There's a parallel architecture and a series architecture again. And in this case, notice this is a high-pass filter, so low frequencies are cut off, and then high frequencies above the corner here, which is again around 800 hertz. The filter outputs basically a pass band, right? The filter has a magnitude response of 1, meaning it just passes everything through. So once again, you can see excellent agreement between the theoretical model and my actual data points. These are the bandpass filters. This is a parallel architecture bandpass filter and a series architecture bandpass filter, and they have slightly different characteristics, but they both work very well as bandpass filters. You can see that the pass band is right around here where the peak is, and at low frequencies and at high frequencies, the filter rejects the signal because it has a low output, low magnitude of the frequency response. And once again, you can see excellent agreement between the model and my actual data. So this is all good news. It says that these filters are simple to build, but they perform as expected, and they can be modeled very accurately using the Excel model. Here's the last slide I'll show you. This is the notch filter. So this is a parallel notch filter here, and this is a series notch filter down here. And remember, the notch filter, what it does is it rejects certain frequencies inside the notch. And so the notch here is around 800 or 900 hertz, something like that. And you can see there, that's where the minimum of the filter frequency response is. And then all other frequencies, it pretty much lets through. So once again, you can see almost perfect agreement between the model and the experiment. So these filters are very buildable. They're relatively easy to build and debug, and also to design and analyze using all the methods that we've learned in this course. So that's it, you guys, for Chapter 6. We now, the course kind of changes gears a little bit, and the next chapter is Chapter 7, which covers sampling theory. I'll see you guys then. Goodbye.